Welcome back. Let's continue our discussion of what this scalable idea means. You remember that we talked about the kitchen and how, similar to a kitchen, we have to give instructions to our machines to produce a result. And in the previous video, we talked about this function, finding Nemo. Let's measure the performance of this function. Well, JavaScript gives us a nifty little tool that comes built in to the browser, which is where we're running this code. So depending on your language, you might not have this option, but you will have different ways of measuring this. Don't get too hung up on this. We want to use this as an example to measure how long it takes for this function to run. We can do this in JavaScript by saying, let's say time 0 is going to equal performance that comes built in to the browser, and we just say now. And this t0 is going to start this timer before the loop happens. And then when the loop ends, I'm going to have another timer called t1, and this is going to equal performance.now. So we have two timers, one at the beginning, one at the end after the function goes through the loop to find Nemo. And then at the end, we'll just do a fun little console.log, and we'll say that the call to find Nemo took, and we can just do a simple t1 minus t0, and then we'll say milliseconds, because it's going to give us the results in milliseconds. Let's see if this works. I'm going to run this code, and let me add a space in here, and we see that it took 0 milliseconds for this code to run. Let me run that again. 0 seconds, again, 0 seconds, 0 seconds. And if I keep clicking it, I see that, oh, now it takes a little bit longer. And that's because this is really fast, right? Our computers, machines are extremely fast in this day and age. And because we're only looping through this once, well, it takes almost 0 milliseconds. And the display just rounds this down. But what if we had a bigger array? Let's say that we have an array over here that has const everyone, and it has all the characters, or at least a lot of the characters from the movie Finding Nemo, which if you haven't watched it, amazing movie, highly recommend it. Anyway, we see that we have a lot more characters now. So instead of just having a single array, let's have the array everyone in here. And this array now has a lot more items. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 loops in here that we're going to do. If we run this, we see that the time is still the same, pretty much 0 milliseconds, sometimes a little bit more, and the time changes all the time. But we don't see that much of a difference, do we? I mean, we went from 1 loop to now 10 loops, but it's still super, super fast. And again, that's because our computers in this day and age are quite fast. The difference between 1 loop and 10 loops is not that big. But let's do a little fun trick here. In JavaScript, we can create a large array. Let's just call it large. And we can create a massive array by just saying new array. And we'll give it 100 items. And this 100 items in the array, we can fill it with, let's say, Nemo. And this is just going to create an array that has Nemo 100 times. So instead of everyone, let's do large and hit run. All right, we see here that it's found Nemo 100 times because, well, we just filled it with Nemo. And at the bottom, we see that it took 0.5 milliseconds. That took a lot longer, didn't it? Let's do even bigger. Let's do 1,000. Hit run. It took 7 milliseconds now. What if we do even bigger? What if we had a massive array of 10,000? If we hit run, 46 milliseconds. It's still pretty fast. And then just for fun, one more. If I hit run, You saw that delay and how long that took. That took 343 milliseconds, or 3.4 seconds. Now, what do we just see here? Well, we see that as our input grew, our function, find Nemo, became slower and slower and slower. Our runtime, how long it takes to run a certain problem through a function, increased. But here's the problem here. If you take this code and run it on your computer, well, your time is going to be different than mine. And I'll leave this code at the end of this video so you can play around with it. You're going to get frustrated because every time you run this code is going to be different than my number. It might be a lot faster or a lot slower. You see, this all depends on how powerful the CPU in the computer is and what other programs are running on your computer, what programming languages you're using, and many other factors. So there's all these factors that play here in our runtime. Therefore, if I speak to my friend across the world, let's call him Johnny, and if I tell him, hey Johnny, my code is so amazing, I've created this find Nemo function and it runs in 3 seconds, 3.2 seconds with 100,000 inputs. How good of a coder am I? And then Johnny says, that's really awesome, but you know what? Mine runs a lot faster. It runs in 1.5 seconds. So I win. What do you think? Do you think Johnny wins? Does Johnny have better code than I do? Well, here's the thing. Not necessarily. This doesn't really mean much. Because it matters what type of computer Johnny has, what other factors, as I mentioned before, the code is running in. So how can we determine who wins? Do I win or does Johnny win? Who has better code? And this is very common in the computing world. We code on our laptops, our computers, but that code doesn't necessarily run on those devices. If we have something like a server, we may have that code run somewhere else on a different computer around the world. So how can we make sure that there's a way for us to measure, in terms of efficiency, what is good code and what is bad code? And what is code that can scale? That as the number of arrays or inputs increases, it doesn't constantly slow down more and more. Big O notation is the language we use for talking about how long an algorithm takes to run. We can compare two different algorithms, or in this case functions, using Big O and say which one is better than the other when it comes to scale, regardless of our computer differences. And we can measure Big O like this. I'm going to warn you that this will look really confusing at first. And this is the first time we're seeing this diagram. And don't worry, by the end of this section, this is going to make sense and you're going to be completely fluent in this. So just trust me in this. Keep following these videos. I know I'm kind of circling around the topic and not being direct as to what it means, but I promise you, by the end of this, this is all going to make sense and you're going to be a Big O ninja. When we talk about Big O and scalability of code, we simply mean when we grow bigger and bigger with our input, how much does the algorithm or function slow down? If the list of characters, let's say elements here, so that is Nemo, so characters in Finding Nemo in our array, as that increases, how many more operations do we have to do? That's all it is. This is what we call algorithmic efficiency. Big O allows us to explain this concept. Remember how in our function we initially had an array of just one, which was Nemo? So that is the number of elements, number of inputs in a function. It was right here. But then as we increased that array to have more characters, and then we created that massive array of 100,000. So as that increases, you saw that the number of operations or the number of things we do in the loop increased over and over. And different functions have different Big O complexities. That is, these number of operations can increase really, really fast, like this one, which is not good. You can see here that it's horrible. and things that are quite good actually and don't increase as much. And we're going to look at examples of different ones and how to actually measure this and what this entire notation means. But to end this video, so we can dive deeper into the topic, just remember this point. When we talk about Big O and scalability of code, we simply mean when we grow bigger and bigger with our input, how much does the algorithm slow down? The less it slows down or the slower it slows down, the better it is. So instead of using performance.now and using time to measure the efficiency of our function, we can just calculate how many operations a computer has to perform, because each operation takes time on a computer. So Big O allows us and concerns us with how many steps it takes in a function. All right, let's dig in deeper and deeper into this topic. I'll see you in the next video. Bye-bye.